What is inside a black hole? In this study, the scientists were able to determine the mathematical description of the quantum state of the matrix model. The American physicist Enrico Rinaldi, along with his team at the University of the Michigan, used quantum computing and computer learning to describe what is believed to be the interior of the black hole. Scientists relied on the holographic principle, which suggests that the two existing theories, particles and the gravity, are equivalent to each other. The complexity of the ideas lies in the fact that they are built in different dimensions. Both theories explain various dimensions, but they differ by one in the number of the dimensions they describe. So, for example, gravity exists in three dimensions inside the geometry of black hole, but particle physics lives in the two dimensions on its surface, a flat disk. Consider the black hole, which, due to its massive mass, wraps space-time. The black hole's gravity, which exists in three dimensions, mathematically connects the particle dancing above it, which exists in two dimensions. As a result, a black hole exists in three-dimensional space but is perceived as a projection of particle. Some physicists or scientists claim our entire universe is a holographic representation of particles, and this could lead to consistent quantum explanation of gravity. In Einstein's general theory of relativity, there are no particles, there is just space-time. And in the standard model of particle physics, there is no gravity, there is just particles, say Enrico Rinaldi. Connecting the two different theories is a long-standing issue in physics. Something people have been trying to do since the last century. A work by Reynolds and colleagues published in the journal PRX Quantum examines how to prove the holographic duality using quantum computing and the deep learning to determine the lowest energy state of the mathematical problems known as quantum matrix model. Particle theory is represented by these quantum matrix models because holographic duality implies that what happens mathematically in a system representing particle theory will also affect a system representing gravity. Solving such a quantum matrix model could yield gravity related knowledge. Ronald and his colleagues employed two matrix models that are simply enough to solve using the traditional methods, yet have all the properties of more difficult matrix model using the described black hole via holographic duality. We hope that by understanding the properties of this particle theory through the numerical experiments, we understand something about gravity and Snell. Unfortunately, it is still not easy to solve the particle theories, and that is where computers can help us. These matrix models are numbers that represent objects in string theory, which is a framework in which one-dimensional strings represent particle in particle theory. Researchers are aiming to determine the precise arrangement of particles in the system that represents the system's lowest energy state, called the ground state. When they solve matrix models like these, nothing happens to the system in its natural condition unless you add anything to it that causes it to be perturbated. It is really important to understand what this ground state looks like because then you can create things from it. Rinaldi says, so for a material, knowing the ground state is like knowing, for example, if it is a conductor or if it is a superconductor or if it is really strong or if it is a weak, but finding this ground state among all possible states is quite difficult. That is why we are using these numerical methods.